focused until I actually write something. We're going to talk about the chemistry of alkenes and alkynes. And more specifically, we're going to talk about chemistry of the pi bond. Oh, it's really out of focus, but don't panic. It's not you, it's me. Oh, there we are. So we're going to talk about the chemistry of alkenes and alkynes this week. And we'll recall that alkanes are comprised of carbon and hydrogen, where all carbon is sp3 hybridized. And so our simplest alkane, our second simplest alkane might be methane, but our simplest two-carbon containing alkane would be ethane. And ethane has only signal bonds, and we did some chemistry last week with ethane. And propane, or any alkane, we can treat it with chlorine and UV lights, or bromine and heat, for example, and radically halogenate. But alkanes have special property that they have free rotation about all carbon-carbon bonds. And another kind of key point about this carbon-carbon sigma bond in the middle, that's about worth 95 kcals per mole. And we learned last week that carbon-hydrogen bonds are about 100 kcals per mole, so a carbon-carbon single bond or a carbon-hydrogen single bond, all about the same energy. They're very, very stable bonds, and this is reflected by things that are about 100 kcals per mole or more. Alkenes, on the other hand, have at least one double bond in them, so they at least have some sp2 hybridized carbons to be called an alkene. And we know that there's some consequences for this. This carbon is sp2 hybridized. All the bond angles here will be 120 degrees. This molecule is flat and planar. All 6 atoms I've drawn here are in the same plane, they're flat. And about this central bond here, there is no free rotation. The presence of this pi bond does something special to carbon-containing molecules, and we'll talk a little bit more about it, so we're going to start off slow before we get into mechanisms and reactions. But the presence of the pi bond does something special. It's no longer able to freely rotate. We know the anatomy of this carbon-carbon bond here is a combination of sigma bonds. So again, this is sp2 hybridized carbon, and there'll be 3 sp2 hybridized carbon-carbon bonds or carbon-hydrogen bonds, and these are all the sigma bonds. But the special feature now of sp2 hybridized carbon is that it also has p orbitals. And in these p orbitals, there's 1 electron each. And these p orbitals actually overlap when they come close together. And it's okay that this drawing's a little messy. It's okay if your drawing's a little messy. If you want a really pretty picture, go back to your textbook. But this pi bond is constructed from the sideways overlap of 2 p orbitals. It's different than how sigma bonds are constructed. Sigma bonds are constructed by the collinear overlap of 2 orbitals. They make very, very strong bonds. So when you make a sigma bond, like the one here or like the one here, 2 orbitals come together in a straight line and they form very, very strong bonds. Pi bonds are definitely weaker. The 2 orbitals involved don't come together like this anymore. They come together like this, and they don't overlap as well. And so this particular pi bond is going to be weaker than a sigma bond. That's the first key point about pi bonds. So they have a sideways overlap, and pi bonds are weaker than covalent bonds. So pi bonds are weaker than covalent bonds. And in ethylene, or ethene, this molecule here, we could either call it ethylene or ethene. Both names are okay. The sigma bond is about 88 kcals per mole in energy. It's a little bit weaker than the sigma bond in ethane. That's okay. It's a slightly different construction. It's the sigma bond that comes from two sp2 orbitals. And in ethane, the sigma bond comes from two sp3 orbitals, so there's a slight difference. But the pi bond is appreciably weaker. It's 66 kcals per mole. So that's either its strength or how much energy requires to break it. So key points about pi bonds. Pi bonds are definitely stronger, or double bonds are definitely stronger than single bonds. This molecule is 95 kcals per mole to break these two carbons. And this molecule here to break these two carbons in half is 88 plus 66. So pi bonds are definitely stronger, or double bonds are definitely stronger than single bonds. But a double bond isn't twice as strong as a single bond. Okay? And it's this key point right here that the pi bond is a little weaker. It has this funny shape or architecture, and this is where reactivity comes into play for these types of compounds and why they're reactive in a very different way than alkanes are. Alkanes are very, 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 three varies, unreactive. Alkenes are much more reactive due to the presence of the pi bond. Let's go back briefly and review some nomenclature on alkenes so that when I'm speaking about some slightly more complex alkenes, you're not completely lost about what I'm saying or some other fundamental properties that you learned with Dr. Marine. It's really simple stuff. So we have ethene, simply a two-carbon containing alkene. We could call this ethene. The eth comes from the two carbons that make it up, like ethane, and the ene part is just the suffix that describes the most important functional group. If we switch gears and add one more carbon, we have propene. This is quite simple. And then when we get to butene, we can have something like 1-butene. 1 describes the location of the double bond. You might have also seen that this could be called but-1-ene. Both of these names are the same. They both have the same exact meaning. I'm not going to ask you to name alkenes anymore, but I'm going to make sure that you can translate something like this into this. That shouldn't be too difficult. If I say propene, you shouldn't draw anything other than this. If I say ethene, or write it down, you should understand exactly that it means this. We have a variety of different butene isomers. We have some stereoisomers here, and we know that this is trans 1-butene, or we might be able to call it trans-but-1-ene, but, a little mistake here. It's Monday. So, difference between 1-butene and 2-butene, I made a little mistake here. We indicate that the alkene starts at the lowest number on the chain, right? Its starting point is at the 1 carbon, and here, either if we go left to right or right to left, we encounter the alkene at the 2 position. And we have a configurational isomer here, or stereoisomer. This would be trans-2-butene. Right? These are stereoisomers. They're fixed, they're locked, the double bond can't rotate. That's why these two compounds are different. You should also recall and start thinking ahead about E and Z. That was another property of alkenes, and we'll briefly approach that particular problem now when we have a tri-substituted alkene. Let's just draw a kind of simple one. We'll put chlorine, fluorine, hydrogen, and a methyl group on it. Cis and trans doesn't make any sense for this particular compound. Cis and trans actually, interestingly, are relative terms. They're relative terms, not absolute terms. We'll get to the difference momentarily. So cis and trans work fine for 2-butene or cis-2-butene. When you say it's cis, it means there's 2 methyl groups on 2-butene if you draw it. And if it's cis, then the 2 high priority groups are on the same side. For here, we don't use cis and trans anymore. You know that we use E and Z. But we could say that the methyl group and the fluorine group are trans to one another, or the methyl group and the chlorine atom are cis to one another, but this is not an absolute term anymore. We have too many substituents now. If we have 3 substituents or 4 substituents, we can't use cis and trans anymore. In this particular molecule, we know that between the two of these, chlorine has the higher priority. Obviously, between carbon and hydrogen, the methyl group has the higher priority. And so we have the EZ rules now, and this is either E or this is Z. And we know that this should be Z, or zusammen, from the German word meaning together. It's an ugly word. The other word, E, entgegen, comes from the German word that means opposites. Right? So if the groups are together, we call them Z. If they're opposite, we'll do an example where we have some groups that might be assigned opposite to one another. Let's put bromine, chlorine, fluorine, and hydrogen. In this particular molecule, bromine is higher priority than chlorine. Fluorine is higher priority than hydrogen. These are opposite to one another, and we say that this has E stereochemistry. We can apply E and Z to simpler things, like these two molecules, but we can apply trans and cis to more complicated molecules like tri or tetrasubstituted compounds. This would be Z, 2-butene, and this would be E, 2-butene if we wanted to. But again, we can't say that this is cis or trans because those are relative terms. You would have to say that the methyl group and the chlorine group are cis to one another. That's very, very confusing. The other way you could say it is simply that this double bond has Z absolute stereochemistry. Okay, so that's just some very, very quick review. You should be able to do that and digest that type of information without any struggle or strife on your part. So easy, it was difficult. Make sure you understand this at this particular point. Okay, it's going to keep using the same sheet of paper